Hi friends, let us start our new section, time dependence of expectation value in quantum mechanics. So here expectation value depends on time. That is, it means expectation value changes with as a function of time. Okay, suppose at t equal to 0, we are taking an observable A. And the initial ket of one of the eigenstate of the observable A, which commutes with H, is ket A dash, or generally we can write like this, ket A dash t equal to 0. Okay, so why this form? It means at a time equals 0, initial time, the system has a state A dash, ket A dash. So we take an observable A and we assume that the one of the eigenstate is ket A dash, or generally like this. Now we are going to consider another observable B, which is not commute with Hamiltonian or A. Okay, and its initial ket we are assuming ket A dash. Just taking the ket A dash is the initial ket of the observable B. Then the expectation value of B can be written as expectation value of B at a time equal to 0 is given by A dash B A dash. Okay. Then put it equation number 1. And after later time t, we are going to check what will be the expectation value of the observable B. So after some time t, the ket becomes ket A dash t0 equals 0 t, like this. Okay, because we already studied about time evolution operator. When a time evolution operator acts on a, that is, this is our time evolution operator. When time evolution operator acts on a initial ket, then it gives ket alpha t naught t, like that. Here our time evolution operator t0, in this case 0 act on our initial ket. What is our initial ket? Ket A dash, that will gives A dash t0 equals 0 t. So after some time t, the ket becomes like this. Okay, so from this we can take the bra of the ket, like bra of the ket, bra A dash t0 equals 0 t equals bra A dash u of t0. Okay, then what will be the expectation value? Later time t, the expectation value of observable B is given by expression value of B at the time t equals, this is our ket, so equals bra A dash t0 equals 0 t B A dash t0 equals 0 t. This is our expectation value, and we know the values of bra and ket. Substituting here, what we get? This is our bra value, bra A dash u of t0 b, and ket value is this value, u of t0 ket A dash. And we studied about time evolution operator, u of t0 equal to e raised to minus I e A dash t minus t0 by h cross, from where we solved Schrodinger equation, and the solution, one of the solution of Schrodinger equation is this. Okay, then here u of t0, so u of t0 becomes e raised to minus e a dash t by h cross. Okay, so substitute the value here. Listen, this is a bra operation, so this plus conjugate will be substituted here. So get bra a dash e raised to plus I e a dash t by h cross into b u of t0 e raised to minus I e a dash by h cross into get a dash. Okay, and when looking to the both the exponential, it get vanishes. So what remains? A dash b a dash. This is our expectation value of observable at the time t, and when compare with equation 1, the both are same, so it is equal to expectation value of b at initial time. So which means there is no change in the expectation value. Expectation value does not depends on time, right? So it means we can write up it means expectation value of an observable b with respect to an energy eigenstate, with respect to an energy eigenstate does not change with time, Okay, here expression value does not depends on time. Okay, so the energy eigenstate, which is this is energy eigenstate get a dash, the get a dash energy eigenstate does not change with time. So this energy eigenstate, so this energy eigenstate is called stationary state, is called stationary state. Okay, then we want the time dependence of expression value, so we consider non-stationary state, non-stationary state. So in the case of non-stationary state, there is many energy eigenstate. Suppose one of the energy eigenstate is get a dash, another one is get a double dash, another get a triple dash, etc. So if you are taking expectation value with respect to superposition of energy eigenstate, then that state is called non-stationary state. That is, are if we are taking expectation value with respect to a superposition of energy eigenstate, we call it non-stationary state, Okay, so in this case that consists of a many energy eigenstate, and we are superposition of energy eigenstates are taking, and find out the expectation value. Okay, so suppose initially we take our initially our eigen state is ket alpha, or we can written as ket alpha t equals 0. More generally we can write like this. That can be represented as expansion coefficient base ket. Any vector can be represented by a expansion coefficient and a base ket. So it gives summation a double dash c a double dash ket a double dash. Okay, this is nothing but c a dash ket a dash plus c a double dash ket a double dash plus etc. Okay, etc. and this is expansion coefficient, this is base ket. Okay, then we are going to take the bra of the get will gives bra alpha t equal to 0 equals summation a dash. Just to show this bra operation, so I would like to write the a dash, ca dash conjugate, and this get bra a prime. Okay, this is nothing but ca dash conjugate bra a dash plus ca double dash conjugate bra a double dash plus etc. Okay, this is our initial state. Initially we take a ket alpha. Okay, and it can be represented by expansion coefficient and base ket. Okay, and take this bra also. Then we can see the expectation value of b at t equal to 0 is what, alpha b alpha, and we know the bra value of alpha is this. So substituting the bra value of alpha, summation a dash c a dash conjugate c bra a dash b into ket alpha value summation a double dash c a double dash ket a double dash. Okay, and this is our value. This is our at t equal to 0. This is our expectation value, multiplication number 2. And at a later time t, we take ket as ket alpha t naught equal to t. Okay, that is ket alpha t0 equal to 0, t equals time evolution operator into ket alpha. When time evolution operator acts on a initial get, we get this kind of get after time t. Okay, and take the bra of the ket gives bra alpha t0 equal 0, t equal bra alpha u t0, and we are going to find out the expectation values. So we are going to find out the expectation value of b, observed b at time t equals alpha t0 0 t into b alpha t0 equal to 0 t. Okay, then we know the values of a bra here and get value here. So put the values. Alpha bra alpha u of t0 b u of t0 get alpha. Okay, then what is the value of bra alpha? Bra alpha value, now this value, put in this value summation a dash c a dash plus conjugate bra a dash left is u t0 b into u of t0 and the ket alpha value is this. So summation a double dash c a double dash ket a double dash. Okay, this is our, and u of t0 we already know. U of t0 value is e raised to minus I e a dash t by h cross. So substituting the value we get summation a dash c, we combine the both summation and c a prime and c a double prime and the value is u of t0 bra a dash u of t0 is bra, so e raised to plus I e a dash t by h cross into b into u of t0 is e raised to minus I e a double prime t by h cross get a double prime, because here a double prime we are used. So what we get, combining this part, summation a dash a double dash c a dash conjugate c a double dash, both can be combined, a dash b a double dash, and we take the exponential. From the exponential we take e raised to minus I outside, so left is e double prime minus e prime t by h cross. Okay, this is our expectation value at time t, and put indication number 3. Then where the omega, where e a double prime minus e a prime by h cross is nothing but omega a double prime a prime, called what we called Bohr's frequency condition. Bohr frequency condition. Okay, so this is omega, this is an oscillating time. Okay, then you have to listen here. When we compare equation 2 and equation 3, what we can observe up to in this case, this answer summation answer up to this same, all are same up to this case, and additional term is this one is our additional term. Okay, so what we can conclude that when we compare equation 2 and equation 3, there is an oscillating term in the equation 3. There is an oscillating term except the initial term. So expectation value of b at a time t equals expectation value of b times 0 into some oscillating terms, Okay, that means what, the expectation value of b depends on time. Okay, which means that expectation value changes with time. This is all about our time dependence of expectation value. Okay, so let us look an example for the time dependence of expectation value is spin precession. Okay, in this case we are going to find out the expectation value of xx, and we will show these expectation value of xx depends on time. Okay, and we already know for any observable a, the expectation value becomes summation a dash mod in the product of a dash alpha whole square, where a dash is measured value and this mode is probability of getting a dash. So through this problem we are going to find out expectation value of Sx, so that will be equals measured value into probability of getting Sx. So suppose consider a simple system where Hamiltonian of a spin-off system with magnetic moment EH cross by 2 MEC subject to an external magnetic field B is H equals minus of E by MEC into S dot B. E greater than 0 for an electron. Okay, and we take B to be static. We take B to be static. Uniform magnetic field in the Z direction. So H becomes minus EBMECSZ. Put it equation number 5. But SZ is commutes with the Hamiltonian. SZ is commute with the Hamiltonian. So the SZ eigenstates are also the energy eigenstate. The energy eigenstate. That is, the eigenstate of SZ will be same as energy eigenstate. That is the meaning of the compatibility. So, and we know the eigenket eigenvalue relation is the eigenket eigenvalue relation is SZ ket plus or minus equals plus or minus H cross by 2 ket plus or minus. Okay, that we already studied. Then the corresponding eigenvalues are the corresponding energy eigenvalues are E equals EB by MEC into, in the place of Z we are substituting H cross by 2. So it gives E plus or minus equal minus or plus E H cross B by 2 MEC. Okay. Let us take omega is a difference in two energy eigenvalue is H cross omega. Let us take omega is difference in two energy eigenvalues is H cross omega. Then omega equal mod E B by MEC. Okay. Then equation 5. Our equation 5 is equation Hamiltonian. Equation 5 gives Hamiltonian becomes what is omega SZ. Okay. Then we know our time evolution operator. U T0 equals e raised to minus Ht by H cross. This equation we also familiarized from Schrodinger equation solution. So putting the value of H here, then time evolution operator becomes U of T0 equals minus I omega SZ T by H cross. Okay. So this time evolution operator contains all the information about the time development. Then here the SZ eigenkets are plus ket minus ket. The eigenkets of SZ are plus ket minus ket, which are using to expand the initial ket, which are also energy eigen ket. That is nothing but we already say that SZ eigenkets are also the energy eigenkets. Okay, so SZ eigenkets are plus ket and minus ket. Then the energy eigenkets also are plus ket and minus ket. Okay, so these eigenkets are using to expand our initial ket. Okay, Suppose we are going to expand initial ket. Okay, suppose at t equal to 0, the system is characterized by ket alpha equals c plus ket plus c minus ket minus. Put it equation number 5. And here when we look in the ket alpha initial ket, this ket alpha initial ket alpha represent what? Represent the spin up state. Represent spin up state, or more precisely sz plus, which means that when c plus equal to 1, c minus equal to 0, the equation become ket alpha equals, this is 1, this is 0, the only term left is ket plus, that is it is in spin up state. But this equation 6 represent, or initially expand initial ket, we are expand using the eigenkets plus ket minus ket, we will get it is spin up state. Okay, then we are going to find out after later time what will be the state. Okay, so at later time t, the ket is, we obviously written as ket alpha t00 t, and which is alpha t0 equal to c0 t equals multiplying by a time evolution operator u t0 ket alpha, and putting the value u t0. What's the value of ket alpha? Ket alpha value from the equation 6 we know the value c plus ket plus c minus ket minus. Okay, then multiplying into inside, what we get equals c plus u t0 ket plus c minus u t0 ket minus. Okay, and we know u of t0 value, we find that where this one, and this value is putting here, we get c plus u of t0 e raised to minus I omega zt by h cross plus ket plus c minus e raised to minus I omega z t by h cross ket minus. Okay, so okay, and we know we already studied sz plus plus or minus ket equal to plus or minus h cross by 2. Okay, so putting the or from this we get sz in the place of sz, we can substitute h cross by 2. Okay, so our ket alpha t0 equal to 0, t equals c plus e raised to minus I omega, in the place of z we are going to substitute h cross by 2. We are going to substitute h cross by 2. So we write like this, because instead of the sz we are substituting plus h cross by 2, and instead of this sz we substitute minus h cross by 2. So ket alpha t naught equal to 0, t equals c plus e raised to minus I omega h cross t by 2 h cross into plus ket plus c minus e raised to minus omega minus h cross t by 2 h cross into minus ket. Okay, and and rearranging it will become c plus e raised to minus I omega t by 2 plus ket plus c minus e raised to plus I omega t by 2 into minus ket. Put it equation number 7. And when compare with our equation number 6, okay, the initial ket is c equals c plus ket plus c minus minus ket. So we when here the two exponential becomes vanishes, so thereby we can write this new later time t, the ket becomes c plus ket plus c minus ket minus equals to our initial ket. That means what? Our state of the spin is in still remains spin up state at later time t. So it is stationary state. Okay, the spin state of a spin does not change with the time. So we need non-stationary state. Okay, so uh, that's why that's why that's why let us suppose that initially the system is in sx plus state, and we studied the relation xx get sx plus or minus equals 1 by root 2 get plus or minus 1 by root 2 get minus. Okay, put it equation number 8. When we compare equation 7 and 8, comparing equations 7 and 8, that implies instead of c plus, what is here? 1 by root 2. So c plus, and instead of c minus, what is 1 by root 2? So c plus and c minus are same as 1 by root 2. Okay, then equation 7 becomes get alpha t naught equals t equals 1 by root 2 e raised to minus I omega t by 2 plus ket plus 1 by root 2 e raised to I omega t by 2 ket minus. Okay, instead of c plus and c minus, we put the values only. Then let us take the bra of this ket. Then the bra of ket sx plus or minus is given by what will be bra sx plus or minus equals 1 by root 2 bra plus or minus 1 by root 2 bra minus. Put it equation number 9. Okay, now we want to find out what expectation value of sx, and we already in the first section we already told that expectation value of sx will be measured value the probability of getting xx. So first of all we have to find out the probability of getting sx. Okay, suppose we know probability. What is probability? If an observable acting on a ket gives eigenvalue and ket a dash. Okay, so probability of getting a dash is nothing but mod inner product of a dash alpha whole square. This is probability of getting this a dash. Then like that we can write probability of getting sx plus or minus. Probability getting sx plus or minus will in the at the initial state or initial state ket alpha, the probability will be equals, probability is mod in the product Sx with alpha whole square. Okay, and we know the value of bra Sx plus. So inside the bracket we put the value 1 by root 2 bra plus or minus 1 by root 2 minus bra minus, and at the value of a ket alpha. Ket alpha we have means value. Okay, ket alpha value is 1 by, yes, the ket alpha. In this ket alpha, c plus 1 plus c plus ket plus c minus ket minus. So instead of c plus, if we put half, here also half, what will be ket alpha? Ket alpha is, putting the values, we get spin up state. In the earlier time we derived spin up. So the initial time it is gives spin up state only. It gives spin up state. Okay, let us look. Okay, after time t, the ket can be written as this one. What? Ket alpha t not equal 0, t equal 1 by root 2 e raised to minus omega t by 2 plus ket plus 1 by root 2 e raised to I omega t by 2 minus ket. Okay, so the probability of getting this ket is the probability of getting xx plus in this case will be at a time t will be mod xx plus or minus alpha t 0 t whole square. Okay, so what you can write, probability of getting sx plus is mod, we know the value of sx, this value, look at bra sx plus or minus equal to 1 by root 2 bra plus or minus 1 by 2 bra minus. So put the value of xx, this bra sx plus or minus here. So what do you get? 1 by root 2 bra plus or minus 1 by root 2 bra minus into, then ket alpha value is here. So put the value 1 by root 2 e raised to minus I omega t by 2 plus ket plus 1 by root 2 e raised to I omega t by 2 into ket minus, okay, mod whole square is left. Okay, so that is equals, when we multiply inside we get mod 1 by 2, first this multiply with the first term, so 1 by 2 e raised to minus I omega t by 2 plus and plus, when this term multiply with the second term, that gives 1 by 2 e raised to I omega t bra plus minus, then plus or minus this term multiplied with 1, first term 1 by 2 e raised to minus I omega t by 2 minus 1 plus 1 plus this term multiplied with the last term 1 by 2 e raised to I omega t by 2 minus 1 whole square. Okay, so this value this term and this term vanishes, only left this kind of terms only. So we get probability of Sx plus or minus equals mod 1 by 2 e raised to minus I omega t by 2 plus or minus 1 by 2 e raised to I omega t by 2 whole square. So this is nothing but we can written as e raised to I omega t by 2 plus or minus e raised to minus I omega t by 2 by 2 whole square. What is this? This is either cos square omega t by 2 or sin square omega by 2. So two possibility, cos square omega t by 2, this is for xx plus, and sin square omega t by 2, this is for x's minus. Put equation number 9. Okay, 9, sorry, equation number 10. Okay, here what kind of conclusion we reached, that is in this probability contains xx minus, that is spin down spin. Okay, so initially the spin is in positive x direction, but magnetic field in the z direction causes it to rotate. Thereby we obtain after later time t we obtain what probability for finding xx minus also, probability for finding xx minus also. So what initially the spin is in positive x direction. Okay, initially spin is in positive x direction, but magnetic field in z direction, causes it to rotate. Thereby later time t we obtain what? We obtain finite probability for finding xx minus. Xx minus means spin down. So at a later time we get spin up and spin down. Okay, so that means it is non-stationary, the state changes. So then our expectation value of xx will be, measured value into probability of getting sx plus. Okay, that is given by here measured value h cross by 2 cos square omega t by 2 plus minus h cross by 2 into sin square omega t by 2. So these are measured values and this is our probability. Okay, we get two probability, cos square omega t by 2 and sin square omega t by 2. So total probability become the sum of the probability. Okay, then when we take outside h cross by 2, what is left inside the bracket is cos square omega t by 2 minus sin square omega t by 2. So this can be written as h cross by 2 What is cos square omega t minus sin square omega t by 2? That is nothing but cos omega t. So this is our probable expectation value of Sx. So this quantity contain oscillating term. Which term? Angular frequency corresponding to the 2 energy eigenstate divided by H cross. Okay, so we get oscillating term omega. That's our angular frequency. That is angular frequency. We get oscillating term omega and angular frequency. Thereby we conclude that expectation value in the case of spin precision depends on time. Okay, that we conclude here. Okay, so this is all about our expectation value depends on time, and a similar operation can be done with Sy and Sz. So similar operation with Sy and Sz shows that Sy expression value of Sy becomes H cross by 2 sin omega t, and expression value Sz become 0. Okay, physically it means that spin precision in the xy plane. Physically it means that spin precision in the xy plane. Okay, so spin precision is a tool for other investigation of fundamental quantum mechanical phenomena, and we now we get two probability. Okay, we get two probability. When we take the sum of the two probability, what we get unity. That is the sum of two probability from equation 10. Unless some probability gives cos square omega t by 2 plus sin square omega t by 2. This is nothing but 1. That is unity at all times. It is agree with the property of a time evolution operator, because we study time evolution operator has a property unitary. So it is agree with our unitary property of time evolution operator. That is nothing but u dagger t naught into u t naught equal to 1. So when we sum up the two probabilities, we get unity. That is, it is agree with the unitary property of time evolution. Okay. Okay, next portion we are going to discuss about neutrino oscillations. It's a lovable example of quantum mechanical dynamics. Okay, so first of all we have to know what is neutrinos. Neutrinos are elementary particles. They are elementary particles with no charge, but very small mass. Very small mass. That is much smaller than that of electron. Much smaller than that of an electron. So much smaller than that of an electron. So neutrinos are elementary particles with no charge, but very small mass, much smaller than that of electron. These neutrinos are occurs in nature in three distinct flavors. So neutrinos occurs in nature in three distinct flavors. We are calling it flavors. Okay, three distinct flavors we can see neutrinos in nature, and from these two flavors are we are taking. So the two flavors identified, two flavors among the three flavors, two flavors identified by their interactions, which may be either with electrons, which may be their interaction may be with electrons. In that case we write nu E. Okay, nu E. Or with the interaction muons, that case we can write nu mu. So among the three flavors we take two flavors that can be identified by their interactions, which may be either with electrons. If it is interacting with electrons, in that case we write that flavor is nu E, or with muons, that flavor we can write that nu mu. Okay, so the ket nu E and ket nu mu are eigenstates. Okay, eigenstate of a Hamiltonian that controls those interaction. Okay, so these are the eigenstate, ket nu E and ket nu mu. These are the eigenstate of a Hamiltonian that control those interaction. So neutrinos have all other interactions. Neutrinos have other interactions. If suppose the eigenstate of a neutrino is ket nu1 is mass eigenstate. Suppose this is mass eigenstate and it has a corresponding eigenvalue E1 for mass m1. For mass m1 it has a mass eigenstate ket nu1 and eigenvalue E1. For mass m2 it has a mass eigenstate nu2 ket nu2 that corresponding have a eigenvalue E2. Okay, that is neutrinos have energy eigenvalue, that is neutrinos have energy eigenvalues correspond to states that have well defined mass. That is neutrinos have energy eigenstate and correspond to the state neutrinos have energy eigenvalues correspond to the state, and the state has a well defined mass m1 and m2. Okay, so the flavor eigenstates are, we already mentioned, these are our flavor eigenstate. Okay, flavor eigenstate. So the flavor eigenstates are ket nu E and ket nu mu. These flavor eigenstates are related to mass eigenstate. What is our mass eigenstate? What is our mass eigenstate? This both of one. Ket nu 1 and ket nu 2. These are mass eigenstates. So the flavor eigenstate related to mass eigenstate are through a simple unitary transformation that is through a simple unitary transformation we can relate flavor eigenstate and mass eigenstate of neutrinos. So that simple unitary transformation is given by ket nu e equals cos theta ket nu 1 minus sin theta ket nu 2. And for muons we can recognize the unitary transformation is ket nu muon equals sin theta ket nu 1 plus cos theta ket nu 2, where theta is mixing angle. Theta is called mixing angle. It's a free parameter. It can be determined only through experiment. This value mixing angle. If mixing angle equals 0, what will be the ket nu e and nu mu? Nu e becomes, what is left? Ket nu 1 and nu mu equals ket mu 2. Okay. So what we can say about neutrino oscillation? Neutrino oscillation is a phenomenon by which we can measure the mixing angle. So neutrino oscillation is a phenomena by which we can measure the mixing angle theta. Okay. So at t equal to 0 initial time, the eigenstate of one of flavor of neutrino is ket nu e. At a time equal to 0, ket nu e is momentum eigenstate of one flavor of neutrino. So at a time t equal to 0, the momentum eigenstate of one flavor of neutrino is basically we taken ket nu e, where ket nu e we know what is cos theta nu 1 minus sin theta ket nu 2. So when we listen to the ket nu e, we can see that it involves what? It involves two different mass eigenstate. One is this, another one is this. It involves two different mass eigenstates component. This component involves different frequencies. This will involves different frequencies. So in here involves two mass eigenstates, and these mass eigenstate component will involves different frequencies. Then it develops relative phase difference. Okay, thereby develop relative phase difference. If the difference in the masses is small enough, then this phase difference can be built up over a macroscopic distance. Okay, if the difference in the masses, if the difference in the masses is small enough, then this phase difference, then the phase difference can build up over a macroscopic distance. So by measuring the interference as a function of difference, one can observe oscillations with a period that depends on the difference of mass and amplitude. Okay, so by measuring by measuring interference as a function of difference, so by measuring interference as a function of difference, one can observe oscillations with a period and this oscillation depends on difference of mass, that depends on the difference of mass and an amplitude. So by measuring interference, we can observe oscillations with a period, and this oscillation depends on the difference of mass and amplitude, and this amplitude that depends on the mixing angle. This amplitude depends on the mixing angle. Okay, then neutrinos are very low mass. Neutrinos, we already mentioned neutrino mass is very small. Neutrinos are very low mass, so they are highly relativistic for any practical experimental condition. These neutrinos are very low mass. They are highly relativistic. Okay, let P fixed momentum. There is a fixed momentum, and m be the mass of a neutrino mass, and E be the energy of eigenvalue. Then the energy of eigenvalue will be given by p square c square plus m square c square all raised to half, and it is approximately equal to pc into 1 plus m square c square by 2p. Okay, if we allow our next state is if we allow next state is if we next allow the state getting nu e to evolve, and then later time t ask what is the probability, then we can see that as later time asks what is the probability that is still appears as a continue, which means initially we have a state is continue e, and after later time t the state is same, getting new E. So the probability is appears as probability of initial state to later time t state, same state, that will be given by 1 minus sine square 2 theta sine square delta m square c raised to 4 L by 4 E H cross C, where we know theta is mixing angle, theta is mixing angle, delta m square equal to m1 square minus m2 square, their uh, differences square of their masses, and L is equal to Ct, which is called flight distance of neutrino, flight distance of neutrino, and is equal to Pc, is nominal neutrino energy. So this is all about our neutrino. So we told about neutrino oscillations. Neutrino oscillations are a lovable example in quantum mechanics. For what is neutrinos? Neutrinos are elementary particles with no charge but very small mass. Compared to electron, its mass is very small, and they are occur in nature in three distinct flavors. Among the three distinct flavors, two flavors identify by their interactions, which may be either with electrons, and in this case we can represent as nu E, or if it is interactive with muons, it can be represented as nu mu. And ket nu E and ket nu mu are eigenstate of Hamiltonian that controls those interactions, and neutrinos have all other interactions. For mass m1, the neutrinos mass eigenstate is ket nu1 and its corresponding eigenvalue is E1. For mass m2, mass eigenstate is nu2 and corresponding eigenvalue is E2. That is, neutrinos have energy eigenstate, energy eigenvalue correspond to states that have a well-defined mass. The flavor eigenstates are nu E, nu mu, related to mass energy eigenstate nu1, get nu2, are through simple unitary transformation. This transformation will be defined already, and where theta is a mixing angles, free parameter can be determined only through experiment. If theta is 0, we can find out the values of a flavor eigenstate. Okay, that corresponds equal to the mass eigenstate. So we can summarize Neutrino oscillation is a phenomena by which we can measure the mixing angle theta, and at time t equal to 0, the one of the flavor of neutrino is we take ket nu E, which is momentum eigenstate, and the momentum eigenstate depends on, or it includes what that includes to different mass eigenstate component that will involve different frequency, then it develop relative phase difference, and if the phase difference in the mass is small enough, then the phase difference can build up over a microscopic distance. Okay, then by measuring, or we observe oscillations, and this oscillation depends on difference of mass and amplitude. Then amplitude depends on mixing angle. So neutrinos are very low mass, they are highly relativistic for any practical experiment condition. Let P fixed momentum m neutrino mass and E is energy of eigenvalue, then that is given by the equation. And if the initial state ket mu E after later time state still appears as ket nu E, then the probability will define by this equation where delta m square L E all are defined. So in this video we discussed about time dependence of expectation value that we found with an example, and another topic neutrino oscillation. Okay, thank you.